Now let's talk about concavity. A function is concave up on an interval AB if the graph bends upward at that interval. So I always look at it as kind of looks like this. We've got like a smiley face. You're positive, you're up. It's concave down, so you're negative, you're sad on an interval if the graph downwards on that interval. So again, kind of think about like a sad face. So if I'm looking at this graph here, I'd say here's where this function is concave down. And then it looks like it's concave, even to here. So it's going to be concave down all here. I can see this going down, but then it actually changes to being concave up here. This is where that smiley face comes in. So you can see it's bending upwards. So again, it's bending up. And then right there, it starts bending down again all the way here. So we'd say the concave up is what's in purple and concave down is what's in green. Now we have a specific name for the point where it changes concavity, and those are called inflection points. So if a function f changes concavity at a point x equals c, then x equals c is an inflection point. All right, so determine the intervals at which the function graph below are concave up, concave down, and any inflection points. Okay, so I can see here, again, concave down means you're bending down, concave up means you're bending up, or you can think of the sad face and the smiley face. So it looks like from here to here, we're concave down. And then I switch right here, so that means there's going to be an inflection point here. And it looks like here we're concave up, again it's bending up, until about right here. And at that point is where it starts bending down again. So I would say that this is concave down on the intervals from negative infinity to negative 2 and from 1 to infinity. I'd say it's concave up from negative 2 to 1. And then our inflection points occur at x equals negative 2 and at x equals 1. Let's look at the relationships of concavity in terms of the function, its first derivative, and its second derivative. So if the first derivative is increasing, that's going to end up meaning that that function, original function, is bending up, so that means the function is concave up. If the first derivative is decreasing on an interval, then f of x is concave down. Again, if you think about that, that means that the derivative is, so this is slowly going down, which is going to cause a bend in the original function. If the second derivative is greater than 0, then the function is concave up. And if the second derivative is less than 0, then the function is concave down. You might be wondering, why is that? Well, we just said a function is concave up if the first derivative is increasing. Well, if that's increasing, picture a graph that's increasing, that's going to have a positive slope. So the derivative of that graph is going to be larger than 0. Here we said the first derivative is decreasing, it's concave down. So if I were looking at the second derivative, which is the derivative of the derivative, we'd say this is going to be decreasing. So if I took the derivative of a decreasing function, a function that's going down, that derivative is going to be negative. So that's why the second derivative is negative, where the function is concave down. So let's look at an example. Given the graph, determine the intervals on which f of x is concave up or down. At which values does f have an inflection point? Okay, so here's our first derivative. So our first derivative, we said where it is increasing is where the graph is concave up. So this first derivative graph is increasing from here to here, And then it's increasing again from here to here. So we'll just say this is 2. All right, so I would say that this function is going to be, so this is like 1/2. This is probably more like 1.5. So let's be a little more accurate with our scale. So we'll label that as 1.5. We'll do it in black. So that's about 1/2, halfway through there. And then halfway from there to there is going to be 1.5. And then that would be 2. And that's -1. All right, so we'd say this is concave up from, it looks like about -1/2 to 1/2. And then again, from 1.5 to infinity. And we'd say this is concave down. So concave, a function is concave down where the function is, a function is concave down where the first derivative graph is decreasing. So this first derivative graph is decreasing. It's going down between, so concave down. So it's going to be concave down from -infinity to -1/2. And then again, it's going to be concave down here. So from 1/2 to 1.5. And where we're going to have those inflection points, that's going to happen where we change concavity. So we have change concavity here at -1/2. And then we change concavity here at 1/2. And then we change concavity here at 1.5. Let's look at another example, but this time with the second derivative function. Okay, so we said that a graph is going to be, the function is concave up if your second derivative is positive. So we can see here that f is going to be concave up where our second derivative is positive. So it's positive from here to here, so from 0 to 2. It's positive from 4 to 6. And then it's positive again from 6 to 8. All right, concave down. So that happens when your second derivative is negative. So your second derivative is negative from 2 to 4. And that's it. Where are these inflection points going to happen? So that's where we change concavity. So we're changing concavity here at x equals 2. And then we change concavity again here at x equals 4.